AC coupling and DC coupling, and why one design may be preferable over the other. I get a lot of questions related to AC versus DC coupling. In fact, there seems to be some misunderstanding of maybe when it would be beneficial to do one over the other, and considerations for your storage system, the battery bank size, the capacity, in other words, and the chemistry of that storage system is also relevant, deciding on which way you want to go here. So let's get started. I hope everybody's comfortable and ready to dig in. So let's just do a recap. I'm sure most of you are experienced installers and you know what DC coupling is, but let's just kind of go over and recap exactly what we're talking about when we're referring to the phrase DC coupling. So on your screen, you see a diagram of a typical grid-connected DC coupled system. When you're DC coupling, the PV supplies the charge controller, and you could have multiple charge controllers, each with their own dedicated array, which in turn regulates to the battery and prevents overcharging. Once the battery's full, the battery voltage is reduced to a float level, which means it's being trickle charged. Solar energy will be used to support the load using the residual of charge current. In other words, during the bulk state, 100% of the PV power is being used to charge the battery. And I'd like to take a moment to mention that that's a very important point related to your battery bank sizing, because depending on the capacity of the battery, you may or may not be able to accept the maximum current from your array as designed. So that's your primary consideration, is your bank appropriately sized to accept all of the current from all of your PV sources that are being supplied through the charge controllers. So even though it is a regulator and it will regulate to the maximum charge rate, and then once you reach the absorption stage, the leftover current will be used to support the load. So if you add up, say you got 360 amp controllers, that's 180 amps. Is your battery bank sized appropriately to accept 180 amps? And that's also going to be related to the battery chemistry. You can typically supply more current to a sealed lead acid battery, for example, either AGM or gel, than you can for flooded. And with lithium, you can typically supply C over 1. So the chemistry is directly related to how much current that you can push into the battery, and also the capacity. So when we talk about reaching the bulk voltage, all of that, so let's say you have a small battery bank. Let's say you inadvertently didn't consider the size of the bank, and you've got more charge controllers that the battery bank can safely accommodate. And this actually happened in Hawaii not too long ago. And there's really no way to program the system to say, hey, let's charge at max charge rate 50% until we reach bulk, and then we'll go ahead and open it up. Really, the only way to do that with the existing platform is to incorporate relays, and which is possible to do. You can program the auxiliary port to close when you reach the bulk level, and that could connect to your additional charge controllers. So that's one way that you can get around having a small battery bank. But just as long as you're aware of that limitation, you won't get into a similar position where you're stuck with having to scramble for a solution because the system wasn't designed properly in the first place. So again, once batteries are full, it's going to use that excess current to support the load, and then once the batteries drop to a float level, virtually all of your available solar will be provided to your load demand, and if there's anything left over, that would be exported, assuming that you're on net metering. So anytime that your load demand exceeds solar production, then your excess power is going to have to come out of the battery. If you're off grid, but when you're connected to the grid, it's going to come out of the grid. The only way to dip into the battery with the XW when you're net metering and selling back is to have load shave also enabled during that period. So anytime that your load demand exceeds your solar production, then it'll go ahead and dip into the battery. But otherwise, it's going to take it off the grid. So the grid support voltage setting is the level at which you want to hold the batteries. So when you're operating in grid support mode, you can either set the grid support voltage at the float level or a little lower, or if you're using our charge controllers, we have a feature called enhanced grid operation. We'll talk about that a little more in the next slide. So Schneider Electric offers two different models of solar charge controllers. We have a 60 amp model and an 80 amp model. The MPPT 6150 has a maximum input voltage of 150 volts DC. That is an absolute maximum, and likewise the MPPT 8600 has an absolute maximum of 600 volts DC. It's a high voltage controller. You must consider your record low temps or your likely lowest temps to calculate your temp coefficient for open circuit voltage. If you're sizing your system toward the upper end of the spectrum, or if you're sizing the array toward the lower end, then you need to consider the warmest temps and the max power voltage, not the open circuit voltage. So going back into enhanced grid mode, so when you're using our charge controllers with our inverters, you set the grid support voltage higher than the bulk voltage by at least 2 volts. And what that does is it tells the XW to follow the output of that charge controller. So what that does is it only uses what's available above a fully charged battery to support the load. It does a better job of keeping the batteries full and ready for a power outage. So our little brother to the XW is the Connect SW, which is available in 2500 watt and 4000 watt models. The 24 volt systems are 2500 watt and 4000 watt. We have a 4000 watt model and 48 volts as well. So grid connected systems that use Connect SW will reduce the draw from the grid commensurate with solar production once the batteries are full. The Connect SW has no cell capability. So once the batteries are full, the solar power cannot be harvested under conditions where PV energy exceeds load demand. So for example, the charge controller has 4 kW of available solar, but the load is only 3 kW and the batteries are full. So this means that the PV output will only be 3 kW because that extra 1 kW has nowhere to flow. DC coupling off the grid. When PV supplies the charge controller, which in turn regulates and protects the batteries from overcharging. Loads will always have priority, so if the PV production is less than load demand, then that additional power requirement will be drawn from the battery. If the PV production exceeds the load demand, the excess will be used to charge the battery. Once the batteries are full, the PV production will be commensurate with the load demand. This means the charge controller will reduce power flow when there's excess PV energy over what the loads can consume because that power has nowhere to flow. Under conditions where the PV cannot keep up with the load demand, the batteries may discharge to low battery cutout unless a backup generator is installed, in which case the XW automatic generator start is highly recommended. And I should take a mention to mention that it is really risky to design off-grid without a backup generator. And you know, I think recently of installers that have done this, and really the only way that is feasible is to have enough PV and enough storage to get you through the worst case scenarios. I mean, even regions that have sunshine virtually all year round, like Southern California, can experience a week of cloud cover. And I've been in there, in the area when that actually happens. So situations like that, again, you're not going to expect the customer to sit in the dark till the sun comes back out. So it's really highly recommended to incorporate a backup generator anytime you're going off the grid. So before talking about AC coupling, we should explain just how a grid tie inverter operates. A grid tie inverter is typically a current source only. They cannot produce a usable waveform, hence they cannot be used for backup. This means if the grid goes down, solar production ceases. These applications typically have net metering, and excess solar is exported to the grid. And that's another thing we should mention too, that, you know, I'm sure a lot of you heard the term grid forming. And that's exactly what the battery-based products we offer, such as XW and Connect SW, are, is they are grid forming inverters. So because they are grid forming, they are able to fool a grid interactive inverter into thinking that the grid is still there. So the question is, why AC couple in the first place? What would be a situation where you would want to AC couple over DC coupling? Well, first of all, AC coupling may be more efficient under certain conditions. However, there are factors that must be considered for the health of the system as a whole. So for example, a customer already has grid tie inverter with PV, and either they're interested in battery backup, or maybe their grid tie inverter has failed out of warranty and they are interested in battery backup. So there are options here. You know, they could go with an AC coupled system, or they could go with DC coupling with our high voltage controller. Both are options, but which one would be better? So many customers, when they're interested in AC coupling, if they already have a grid tie inverter, you know, they probably are going to want to know what the differences in efficiency are, and that is going to be one of the main considerations that I hear for the most part is installers believing that AC coupling is the more efficient way to go, and it can be. It certainly can be. That does require that certain other conditions are true, though. So when you're AC coupling, the PV power must occur when the load demand is present to get the maximum efficiency. The losses associated with DC coupling are the efficiency of the charge controller plus the efficiency of the inverter. This is typically around 90% when you add the two. Grid interactive inverters are typically above 96% these days. So how will the system change by AC coupling is the question. So here on your screen, you see a typical grid tied system where you have a main panel, you have a grid tie inverter with the PV feeding the grid tie inverter. So if the grid goes down, then you lose all power to your load, and the grid tie inverter also goes down. It cannot produce power if there's no grid to add current to. So here we can see a system that is AC coupled. And all we've done is we've merely inserted XW hybrid with the battery, and we've also installed a separate and dedicated sub panel for the critical load. So here we would have your non-critical loads dedicated to the main panel. So the grid goes down, you lose those. And then our sub panel would have our critical loads dedicated to it. And also you would have a breaker that was supplying the PV inverter. So the grid goes down, the inverter switches to battery power, and it fools the grid tie inverter into thinking that the grid is still there, allowing it to come online and continue to produce power. So here we can see a functional schematic of an AC coupled system. AC coupling, again, means that the grid is merely passing through the XW. So anytime the grid is present, it's passing right on through. The term selling as it relates to the XW is defined by enabling grid support. And that's typically done when you're DC coupling, because you have an external source of power that's dumping power into the battery, and then the XW is drawing off that same battery to prioritize the load, and if there's anything left over, it'll push it back toward the grid. Now, it is possible to load shave and even sell when you're AC coupling. You can utilize that stored energy to assist in supporting the load and even exporting excess energy back to the grid that has been stored in the battery, say during peak hours. That is possible to do, but the downside of that is, if you have an outage when your batteries are discharged, you're not gonna have much to work with in the event of an outage. And if it occurs during non-solar hours, then you're really going to be at the mercy of how much energy is in the battery, unless you've taken that extra step to incorporate a backup generator, which I think is great for a last line of defense, even with a grid connected system. So the Connect SW can also be used AC coupling. And again, there's nothing to prevent the excess power from flowing back to the grid. So even though Connect SW does not have a cell function per se, in an AC coupled scenario, that power would be used to flow right back to the grid. There would be nothing in the Connect SW from stopping that from occurring, because it's simply a built-in transfer relay. Both platforms, when that internal relay closes, the input and the output are common. This also brings up another point for customers that are in Hawaii or California, and that is the new rules for smart grid interactivity, such as UL 1741 Supplement A, Rule 21, and HECO. These are smart grid functions, and the question is, will AC coupled systems be allowed permission to operate if we're merely inserting a battery-based system between the grid and a compliant inverter? My take on that is that why not? I mean, if the XW or the Connect SW is merely acting as a gateway to pass the grid power through and has no bearing on interacting with the grid whatsoever, it's just there to provide backup so you can AC couple. I don't know why that would be denied, but it's certainly a question that remains to be answered, and it's going to be one that I'm going to be following closely. So here we can see what happens in the backup scenario. The internal transfer relay is open. The connection to the grid is completely isolated. And we are grid forming from the battery, and we're fooling the grid tie inverter into thinking the grid is still there, thereby allowing that PV to flow. So what's going to happen is whenever the load demand is minimal, then virtually all of that PV is going to flow through the output of the inverter into the battery, and that's going to go into the battery unregulated. And that's an important point because you want to make sure that, again, your battery bank is sized to accommodate the total current that could flow into it. So for example, if you have a 4 kilowatt array and you divide that by the nominal battery voltage is 48, that would give you 83 amps of DC current that could potentially be pushed into the battery. So it needs to be sized to accept that total current, at least that total current. And then once it reaches the bulk voltage, the XW or the Connect SW, for that matter, the AC coupling feature will shift the frequency up. And that is designed to curtail the grid tie inverter if that grid tie inverter has curtailment capability, or if it's a standard UL 1741, then it'll shut down and it'll count down for 5 minutes and then it'll reconnect. So if it does have curtailment or an off-grid mode, then it will throttle down the output commensurate with the load, and then it will also provide a 3-stage charging in that mode. So that's really a great feature to have. However, I guess the challenge there would be, you know, if you're grid connected, then you're going to typically be UL 1741 or even UL 1741 SA compliant. So let's say you have convinced the local authorities in Hawaii or California to allow you to AC couple with a UL 1741 SA compliant inverter, and the grid goes down, and then the shifts the frequency up. Well, the part of the new smart grid functions is frequency ride through. So that range is typically 62 to like 68 hertz. So allowing the voltage, or the frequency rather, to increase that high would have a negative effect on loads. To me, to do this, you need to incorporate a disconnect relay. So once you reach the bulk voltage, it'll go ahead and send a signal out the aux port of the XW to disconnect the grid tie inverter from the AC source until you drop to a clear level. And that way you're protecting the batteries from being overcharged. And that also brings up another point as well, is, you know, if you're AC coupling off grid, then you want to make sure that your battery chemistry is going to be tolerant of ramping up to bulk and then shutting down if you're using a grid tie inverter that does not have an off-grid mode. Typically, a lithium chemistry is well suited for partial state of charge, or you know, ramping up to a certain voltage and then stopping. They're pretty much tolerant of different charging algorithms, whereas a lead acid chemistry, many times their warranty is dependent on receiving a proper 3-stage charge regularly. So that's another thing to consider if you're thinking about designing an off-grid system. So again, we're talking about frequency shift algorithm. Here we see an XY chart for the function of frequency shift when using a grid interactive inverter without curtailment capability. We see that the inverter is at full power according to real-time solar production, while the frequency is within the UL parameters. When the battery voltage reaches bulk, the XW plus output AC frequency starts to increase. So if you're talking about a UL 1741 grid tie inverter at 60.2, I believe, it will shut down and it'll go into a countdown and it'll restart. So virtually any UL 1741 inverter will behave in that manner when the frequency shifts up. And again, we're referring to using an external disconnect relay if you have an inverter that can tolerate higher frequencies, such as UL 1741SA compliant. And then, of course, SMA is the only grid tie model that I'm aware of that has what's called an off-grid mode. So they can be used off-grid with our inverter to provide a 3-stage charge if set up correctly. So AC coupling with a generator, that's an important point because typically you're not going to want to export power back to the generator. Generators are not going to appreciate having their armatures spun backwards. So under no load conditions or low load conditions or negative current conditions, then it's going to be important to incorporate an external means of disconnect so that anytime the generator starts, the AC power is removed from the grid tie inverter. So you can use a simple relay with an AC coil, 120 volt AC coil, and use line to neutral of the XWs on the generator input. So anytime that generator is called upon to start, it's going to be because the batteries are low, typically. And so we want to make sure that the grid tie inverter is disconnected so that we don't run into a situation where the batteries are charged and the PV exceeds the load demand. It has nowhere else to flow but back to the generator, and that typically would not be a good thing. So as far as scalability goes, when you're AC coupling, it's important that PV power does not exceed the XW system continuous power rating. So for example, if you have 3 XWs, that would give you, say, 18 kW continuous at 40C, and or 20 kW at 25C, and you have less than 20 kW of PV inverters, then that's acceptable. The problem comes in when customers want to have, say, a single XW 6800 watt and they want to AC couple 12 kW. Well, the problem that arises is that since the XW cannot regulate when being supplied through the output in a backup scenario when you're AC coupling, then all of that power is going to try to get exported into the battery. And that's going to cause an overload condition. It's not going to hurt the XW, it'll just shut down due to overload. So that's the limitation there, is you got to make sure that the amount of PV watts does not exceed the continuous watt rating of the XW system. We also want to take a moment to touch on the 60 amp power limitation of the internal transfer relay built into each XW. And I think there's a lot of misunderstanding in that regard as well, because you know, 60 amps is the allowable pass through. The actual relay itself uses 30 amp contacts, but there's 3 in parallel. So the problem comes in is with surge loads, such as motors, refrigerators, freezers, anything with a motor has a startup current. Locked rotor amps is typically what you want to refer to. So when you have many motor loads starting, especially simultaneously, then we can get up typically between 5 and 7 times what the continuous current rating of that motor is just for startup. So when you're configuring multi-unit systems, they don't all close their internal relays at the same millisecond in time. It's close, it's within a half second, but still, if you're trying to switch more than 60 amps, especially considerably more than 60 amps, then it's going to stress the relay that closes first. It's going to actually cause an overcurrent condition across that relay. Now that said, if you're designing a multi-unit system that is off-grid with a generator, then certainly you could have a situation where your XW system is transferring power at least once a day, maybe even multiple times a day. So that is a situation where you are really going to need to be cognizant of that 60 amp limitation, because you're doing a lot of switching. And when you're passing through more than 60 amps and you're switching many times per day, or once a day even, over time, that's going to result in premature wear on the relay. And if the current level is high enough, then it could even weld the relay shut. So we really want to be careful there. Now, most areas of the U.S. and grid-connected systems have a very reliable grid. You're not going to experience outages, but very rarely. And so that's something else that you might consider if you wanted to design a system that maybe was kind of pushing the limits of the 60 amps, or maybe exceeded that value slightly. The actual lock rotor amps of the individual relays is 75 amps. But again, we have to consider what each relay can do and not the combined total, just because there is a slight delta between their individual closures. Another thing too that is often necessary is with very large inductive loads, incorporating either a soft start or a variable frequency drive helps to minimize that initial startup, and goes a long way in protecting those relays from damage and premature wear. So AC coupling off the grid. AC coupling is a popular choice for existing grid-tied systems that want backup. Customers who want to AC couple off grid have more to consider. Will the charging profile follow the battery manufacturer's recommendation for max charge rate and the proper absorption stage? That's the first question. Is there going to be a backup generator available? Why not just DC couple? If you're specifying an off-grid AC coupled system, make sure the grid time inverter has curtailment capability, or make sure the battery type that you select is partial state of charge tolerant. Some manufacturers of lead acid chemistries, as we mentioned, require a full charge to maintain their warranty status. So be sure that the battery life will not be adversely affected by repeated bulk charge cycles. So here's a chart, and we can see, and this is kind of goes to the question of efficiency. Because a lot of people say, oh, you just get much better efficiency when you're AC coupling. Well, that's true under certain conditions. Here we see an example of a real load profile. We don't know what the state of charge is in the battery when the day started, nor do we know the capacity. This is just related to load and PV availability. Now, so we can see that much of the load demand, most of the load demand rather, is occurring outside of solar hours. So this does not allow you to gain any advantage when you're AC coupling. Now, if we move all those loads into solar hours, then absolutely we're getting much better efficiency, because that power is passing directly to the load. In other words, we're not storing the energy. That's where the efficiency advantage of AC coupling kind of takes a little bit of a nosedive. Here we can see efficiency graph for the XW charging. So you're up around 95% when you're at around 3 kW. 4 kW it starts to drop off, or actually 30% of total. And then when you get up to around 100% of the output capacity of the XW, then you're going to get around 90% efficiency. So what that means is if we're AC coupling and we're storing that energy rather than consuming it in real time with the load, the magnitude that we're charging the battery with that AC coupled power is going to be directly related to the efficiency. And likewise, the inverter efficiency is really fairly similar to the graph that you see here. So you storing the energy, you're getting losses, and then when you're discharging, you're also getting losses. So it's important to realize that when you're designing an AC coupled system off grid, and you want to just make sure that your loads are occurring during solar hours. So here we can see efficiencies for MPPT 60 and MPPT 80. And clearly, if you are DC coupling, then you're getting better efficiency for those loads that are possibly occurring during non-solar. In other words, you're storing that energy for use at a later time. So managing customer expectations, that's probably the biggest thing that we need to consider, especially when we're talking about AC coupling. I think of a customer that I dealt with fairly recently who was concerned because his battery level state of charge on the XW showed 3 LEDs. Which that particular graph is completely based on, or the LED sequence is based on battery voltage. So if you're familiar with the XW, when you're AC coupling, typically you are not using grid interactive features, or if you are, then you have to use two-stage no float. So in other words, if you use 3-stage in the XW and you charge through bulk absorption and float, it'll just keep the batteries at float indefinitely. It won't enter any grid interactive mode unless you set it for 2-stage. So it goes through bulk and absorption, then it's ready to draw from the battery during the load shade period or even through the cell period. So when you're AC coupling, you've got, and you're using those grid interactive functions, then once it goes to AC pass-through and it stops charging, then the batteries are going to be resting. They're not going to have any load on them, but they're also not going to have any charging source applied to them. So a 48-volt battery at rest is typically going to be around 50.8, maybe 51 volts. So that's why the LEDs are showing what most would consider a partial state of charge, but it's really not. So that's where the Connect's battery monitor really comes in handy, is it's going to reflect the actual percentage of current that's been replaced into the battery, and it's not going to be reliant on whether you're at a resting voltage or being held at a float level. So when you're considering grid connected systems, determine how much backup power the customer needs. They may wish to back up the whole house, which is possible with up to 4 XW6848 units. Or if the customer already has a grid tie inverter, then AC coupling should not be an issue, but it's always best to check with the AHJ when it comes to installing a battery-based system. If the customer wants to back up a portion of the house, yet has multiple grid tie inverters, you can AC couple only 1 or 2 of those inverters, not to exceed the rating of the battery-based system, and dedicate the rest to the main service panel. It's also possible to AC couple and DC couple. If a customer lives in an area where the grid is prone to frequent outages, it is usually best to design a DC coupled system. Certainly certain battery types may have a reduction in battery life if proper 3-stage charging occurs only randomly. if the customer has an existing PV system, AC coupling may make sense and be more cost effective. And then, of course, designing around the 60 amp limit, we discussed, multi-unit systems. Here we can see the use of what we call a whole house transfer switch. So this allows you to get around the 60 amp limitation because you're only connected to the input when the grid is present, and you're actually exporting your solar energy to mitigate the demand from the grid. And then if the grid goes down, all the load is transferred to the output side of the inverter. So this is the preferable means of installing multi-unit systems that exceed 60 amps continuous, and we want to protect those internal relays. So I'm not sure how many of you are familiar with our multi-cluster design, but if you go to sesolar.com and under the XW section, download section, you'll see technical publications, and that's where you'll see the XW multi-cluster design guide. This typically focuses in on multi-unit systems, explains the transfer relay limitations. It gives you best practices for designing larger systems for mini grids and whatnot. Offers single phase and three-phase solutions. So now we're going to take a minute to kind of showcase some existing systems that are in the field. Here we see an off-grid system that consists of two MPPT 60s and dual stacked 4048s, connects to SW. This is in Newfoundland, Canada. One of the first XW systems to incorporate the external combiner was and is a system on Appledore Island off the coast of Vancouver. The challenge was to offset diesel fuel consumption for an off-grid retreat. This solar system is reportedly saving $10,000 a year in fuel costs. Here we see a AC coupled system in San Juan Capistrano. We've got two 5 kW Sunny Boys with a triple XW 6848 system. I don't know if you can see in the picture on the right there in the background, you've got the Unity 2 Deca batteries. This system actually qualified for California's SCHIP program and conducted a 2-hour discharge test and got a tidy rebate for that. The Deca Unity 2 batteries actually exceeded my expectations for capacity. So, just kind of a thumbs up for that particular make and model of battery. Here we can see XW MultiCluster that is located in Irvine, California, incorporates 9 XW plus 6848 configured for 120/208 three-phase. We have 3,200 amp hours of lithium iron phosphate capacity provided by Iron Edison. And of course, you'll see the AC combiner there at the forefront. So this provides a point of interconnection and bus bars for the XW system, which is bidirectional in function. Here we see the DC coupled system at Institute of Technology in Chicago. And this system actually provides backup for a gymnasium and their lighting in the gymnasium. So we got 3-phase, 2 inverters per phase, 120/208 and 6 MPPT 80 high voltage charge controllers. Here we've got the legacy model XWs on Appledore Island in New Hampshire. This system incorporates 3 6-unit 6848 3-phase systems. and each also incorporates 8 of our MPPT 80 charge controllers. And you can see down there toward the bottom, the Absolite valve-regulated lead-acid batteries are specified for this system. Some of our
formerly known as juice box, they've been producing lithium-ion solutions since 2013. They are integrated, which means
the Adera Power is a partner of ours that uses the XW. Their lithium manganese cobalt battery, I believe, is the chemistry that they use. They have a proprietary monitoring BMS for use with our product, indoor, outdoor rated, supports AC and DC coupling, does peak shifting. Adera Power, formerly JuiceBox, is one OEM. Another battery type is the lithium iron phosphate solution, is the Discover Energy solution out of Vancouver, Canada. Those are actually plug and play ZAN bus integrated batteries. So that's a really useful function. Customers, I've gotten a lot of feedback that, hey, you know, programming for the battery type and capacity really causes a lot of angst. You know, they don't want to have to go through that step, and plug and play compatibility really adds a lot of value to not only the installer, but to the end customer. There's really no configuration that's required as far as battery programming goes. And of course, Iron Edison is another battery manufacturer that offers lithium iron phosphate solutions and nickel iron solutions. And their batteries, the lithium iron phosphate, are considered drop-in replacements for lead acid chemistries. So as long as you're setting up the XW or Connect SW according to their recommendations, then there really is no integration that's required for their battery chemistry. Highly scalable, and you've got lifetime tech support. They have their own integrated BMS in the battery pack themselves. And then Simplify Power, finally, is another drop-in replacement for lead acid battery. They don't have any comms, but the BMS is built into the battery, and there is a breaker also situated on the same battery. So again, as long as you're setting up the battery according to their recommendations for charge voltage and max charge rate, then it's considered, you know, compatible, and there's really no additional steps to take in that regard. And I understand we've not left too much time for questions, Hannah, but I'll go ahead and turn it over to you. If you want to read me back any questions from the audience, I'd be happy to answer those in the time that we have left.